Induced EMF, electromotive force. Electromotive force is actually a potential difference between 2 points that is measured in volts. It is not a force, but it is a historical term that has not gone away. Because it is an unfortunate name, it is frequently just referred to as EMF, or epsilon. In the unit on electric current in circuits, it represented the maximum possible voltage from a battery, before it was reduced by the battery's internal resistance. It was the advertised voltage of the battery. This chapter will show a way that a voltage can be developed in a conducting wire that is not connected to a battery. In the magnetism unit, it was shown, due to the work of Oersted and Ampere, that a current will generate a magnetic field. After this discovery, physicists looked to see if the reverse could be true, whether a magnetic field could generate a current. Michael Faraday made this connection in 1831, but the magnetic field had to change, either in magnitude or orientation to the wire, where the current was being created. The loop of wire on the left has no battery. It has no power source. It is only connected to an ammeter, which tells you if current is flowing and how much. When a magnet is moving into or out of the loop, the ammeter will show that there is current flowing in the wire. However, if the magnet is held stationary, the current is zero. Michael Faraday connected a battery to a metal coil via insulated wires. So here we have one loop, goes around this way, and all of these loops here just amplify the effects. So there's one loop, and that is connected to a battery. Here's a second loop that has a coil in it, which just amplifies the effects, and it's attached to an ammeter. So it's going to read if there's current, but there's no power source over here, and no current is flowing through this ring at all. What's important is that this loop is close to this loop. So he found that a current would be induced on the right in this loop when the switch in this green loop was opened and closed. If you opened it, you would get a blip over here. If you closed it, you would get another blip in the other direction. There is zero current on the right side when the current on the left side was steady. What that means is that if you close the loop and it's just on, then you would not get any current over here. You only get a little blip on the meter right when the switch is closed, not afterwards. When the switch was closed and the battery was connected, current was then flowing through this loop over here. Right when the switch closes, this meter over here in the purple loop did a little blip. It showed that current flowed right when this switch was closed. However, after the switch has been closed for a little while, this ammeter reading goes back to zero. There's no longer current flowing over here in the purple loop, even though there was still current flowing in the loop with the battery. All right, so the battery is connected, and then you open the switch here. So you're disconnecting the battery. Right at that instant, you get a blip over here in this loop of negative current. That indicates that the current is flowing in the opposite direction that it was flowing before, in this case, clockwise. After the switch had been open a short time, then the ammeter once again went back to zero. There's no current flowing in either loop at that point. When the loop with the battery changes its current by either opening or closing this switch, it generates a magnetic field, which we learned last unit, right? When we have current flowing, we have a magnetic field around it that wraps around. This changing magnetic field induces a current in the second nearby loop. However, current is only generated in this loop over here when this magnetic field acting on it is changing. Steady current generating a steady magnetic field does not induce currents in nearby loops of wire. Here's a picture of Faraday's disc generator. By spinning this metal disc between the poles of a U-shaped magnet, so here we have like a horseshoe magnet, and this disc goes right in between. The points on the disk see a changing magnetic field as they go through the horseshoe. So it's going to have the maximum field when the points are right in between the poles, and then zero field all the way over here. An EMF, and hence a current, is induced in the disk, which will flow out of the machine via these two terminals here. A bar magnet that moves towards, through, or away from a loop of wire will generate an EMF and then therefore a current in the loop. A current is also generated if the loop rotates about an axis that is perpendicular to the magnet. We'll explain that further later on. If the magnet is held here steady, not moving, and the loop's not moving, no current is generated in the loop. It's now time to explain what's going on. There is a difference between this phenomenon and when a current generates a magnetic field. A steady current will generate a magnetic field. If you have a wire with current flowing through it, then you do have a magnetic field around that wire. However, a steady magnetic field and a non-moving, constant area loop of wire will not result in a current in the wire. So if we have a bar magnet here with a north and south pole, we have a loop and they're just there, sitting there stationary, no current is going to be flowing through this wire. A constant magnetic field and a moving loop of wire, so if you move the loop towards or away from the magnet, that will result in a current. And you're going to get a current in different directions based on if you're moving the loop towards or away from the magnet, which we'll get into later. A changing magnetic field in a stationary loop of wire will also result in a current. So that would be like moving the bar magnet back and forth while the loop stays stationary. Also, a constant magnetic field in a changing area of the loop of wire will result in a current. So if this loop, so if you have a bar magnet here and you have a loop of wire and the loop somehow gets larger, so the area inside the loop is changing, you also get a current in the wire. A constant magnetic field and a change in the orientation of the magnetic field relative to the loop also results in a current. So here's an example. We have a bar magnet and we have a loop of wire that's spinning like this. And we're going to see why that will generate current later on. We need to define magnetic flux before we can fully understand this phenomenon.